Hello dear friends, this is the third video in our Management of Information series. For more videos, please visit my Facebook page, Healthcare Quality. In the last videos, we tried to answer the questions why information systems are used and also what components compress information systems. In order to answer the third question, which is how information systems created, we should give a good illustration of the information system infrastructure and database. We will start with information technology infrastructure. Information technology infrastructure consists of four components. 1. Business activities. 2. Platform resource. 3. A data resource. And information systems, as shown in this figure. Business activity framework represents the business activity of an organization and the automation of those activities into business processes. It's the most dynamic framework in the infrastructure because it's closest to the changes that occur in the business world. Any change in the business world usually results in a change to one or more business activities. Platform resource framework represents the hardware and system software. It's responsive to the demands for storing, retrieving, processing, and communicating data. The goal of the data resource framework is the cooperative management of an enterprise-wide data architecture that ensures readily available data to support the enterprise's mission goals and business activities. It consists of three components for data management, data architecture, and data availability. The data management component contains all activities related to management of the data resource. The goal of the data resource management component is to develop a plan for building and managing a formal data resource that will lead an enterprise toward control of its data. It consists of four activities: enterprise resource, management principles, cooperative management, and business integration. The data architecture component contains all activities related to describing, structuring, maintaining quality, and documenting the data resource. The goal of the data architecture component is to develop an organization-wide data resource of well-described, properly structured, high-quality data that are properly documented. It contains four activities: data description, data structure, data quality, and data documentation. The data availability component contains all activities related to making data available while properly protecting and securing those data. The goal of the data availability is to provide easily accessible data that are properly protected, adequately secured, and effectively and efficiently used. It contains 4 activities: data access, data privacy, data security, and data use. The fourth component of the information technology infrastructure is the Information Systems Framework. It represents integration of the business activities, data resource, and platform resource needed to support an organization's business strategies. Now we come to a brief illustration of the structure of databases used in information system technology. Interrelated data extracted from various sources stored for use by the organization. Internal data, usually from transaction processing systems we will discuss later. External data from government agencies, trade associations, market research firms, and forecasting firms, and private data or guidelines used by decision makers. There are 3 structures of database systems: hierarchical, network, and relational. The relational model is the one most widely used, and the other 2 are of historical value. This is an illustration of the relational model. As we see, it consists of tables. Each table has its own fields in the form of vertical columns and its records in the form of horizontal columns. Each record has its own unique key. We have relations between these different tables. We have forms to control input and reports to control output. Queries are used to extract a special set of data from these tables. Rules of data normalization. The first rule is to eliminate repeating groups. In this example, we have the original member list. Each member name is followed by any database that the member has experience with, in addition to his company and company location. First rule is to eliminate repeating groups. In this example, we have the original list of members' name followed by its company. To answer the question, who knows database 2, we need to perform an awkward scan of the list, looking for references to database 2. Some might know many, and others might not know any. This is inefficient and an extremely untidy way to store information. Moving the known databases into a separate table helps a lot. Separating the repeating groups of databases from the member information results in the first normal form. The member ID in the database table matches the primary key in the member table, providing a foreign key for relating the 2 tables with a join operation. Now we can answer the question by looking in the database table for DBase 2 and getting the list of members. The second rule of data normalization is to eliminate redundant data. In the database table, the primary key is made up of the member ID and the database ID, but the database name depends only on the database ID. The same database name will appear redundantly every time its associated ID appears in the database table. Suppose you want to reclassify a database. Give it a different database ID. The change has to be made for every member that lists that database. If you miss some, you will have several members with the same database under different IDs. This is an update anomaly. Or suppose the last member listing a particular database leaves the group. His records will be removed from the system and the database will not be stored anywhere. This is a delete anomaly. To avoid these problems, we need second normal form. To achieve this, separate the attributes depending on both parts of the key from those depending only on the database ID. This results in two tables: database, which gives the name for each database ID, and the member database, which lists the databases for each member. Now we can reclassify a database in a single operation. Look up the database ID in the database table and change its name. The result will instantly be available throughout the application. The third normalization rule is to eliminate columns not depending on key. The member table satisfies first normal form. It contains no repeating groups. It satisfies second normal form since it doesn't have a multi-valued key. But the key is member ID, and the company name and location describe only a company, not a member. To achieve third normal form, they must be moved into a separate table. Since they describe a company, company code becomes the key of the new company table. The motivation for this is the same for second normal form. We want to avoid update and delete anomalies. For example, suppose no members from the IPM were currently stored in the database. With the previous design, there would be no record of its existence, even though 20 past members were from IBM. The fourth normalization rule is isolate independent multiple relationships. The way this situation starts is by a business request list, the one shown below. This could be any two MM relationship from a single entity. For instance, a member could know many software tools, and a software tool may be used by many members. Also, a member could have recommended many books, and a book could be recommended by many members. So, to resolve the two MM relationships, we know that we should resolve them separately, and that would give us the fourth normal form. If, however, there were distinct links between all three, such as that, we would be stating that Bill recommends the Irwin Bible as a reference for Irwin. Then separating the relationships into two separate associations would be incorrect. In that case, we would lose distinct information about the three-way relationship. The fifth normalization rule: isolate semantically related multiple relationships. Okay, now let's modify the original business diagram and add a link between the books and the software tools, indicating which books deal with which software tools, as shown below. The solution, as before, is to ensure that all MM relationships that are independent are resolved independently, resulting in the model shown below. Now, information about members and books. Members and software and books and software are all stored independently, even though they are all very much semantically related. Thank you.